A shadow sits in the oldest light in space tonight. Deep over Antarctica, a particle seems to rise the wrong way through Earth. Inside quiet equations, reality keeps splitting without asking permission, and the people paid to doubt wild ideas are the ones who cannot fully shut this door. If you come here for space stories that sound impossible but stay honest, subscribe now. Join the people who want the strange part and the real part at the same time, because this mystery gets bigger every time science tries to make it smaller. For a long time, the universe felt simple in one very basic way. There was one sky, one history, one timeline, and one shared stage where everything happened. Stars were far away, planets were rare, and human life looked small, but reality itself seemed single. No matter how huge the cosmos became, most people still imagined it as one complete thing. Then modern physics arrived and started breaking that comfort apart. And it did not do this with fantasy or guesses pulled from nowhere. It did it with math that kept working, experiments that kept succeeding, and observations so exact they changed how we see existence. And hidden inside some of those successes was a possibility that sounded almost rude. Maybe one universe is not the full story. That idea goes by many names. Some people say parallel universes, some say multiverse, and some say many worlds. And the names are not all exactly the same because different branches of science imagine the extra realities in different ways. But the core thought is simple enough for anyone to grasp. Our universe may be one part of something much larger. This matters because the question is not just about science fiction fun, and it touches the deepest things science tries to explain. Why does the universe have the rules it has? Why does the early cosmos look the way it looks? Why does quantum physics behave so strangely? And why do some of our best theories keep allowing more reality than we can directly see? Now, to be fair, we need a clear starting point. Scientists have not announced final proof that another universe has been photographed, mapped, or directly visited. There is no clean public moment where the world's physicists all stood up together and said the case is closed. That is not where we are, but that does not mean the idea is empty, dead, or silly. The real reason this topic refuses to go away is much more interesting. Different areas of physics, built to answer different problems, keep pointing toward versions of the same shocking possibility. Not one field, several, not one random guess. Repeated openings. It is like walking through a house and finding several different doors that all seem to lead outside the same hidden wall. To understand why, we have to begin with something very old. Not old like dinosaurs, not old like Earth, but old like the first visible chapter of the universe. A faint glow still fills all of space. That glow is called the cosmic microwave background, which is just a long name for ancient light left over from the early universe. This light was released when the universe was about 380,000 years old. And that sounds ancient to us, but in cosmic terms, it was still very early. The universe was once too hot for light to move freely, then it cooled enough for atoms to form, and the trapped light finally escaped. Today we can still detect it, stretched out into microwaves by the expansion of space. Scientists treat that old light like a record from the baby universe. It tells us what space was like long before stars and galaxies fully formed. Missions such as NASA's WMAP and the European Space Agency's Planck spacecraft mapped that glow across the sky. By studying tiny changes in its temperature, scientists learned how matter was spread out in the beginning. Those small, uneven spots later grew into galaxies, clusters, and the giant web of the cosmos. But before we get to what the sky map did and did not reveal, we need to step even deeper. We need to go to the quantum world, the tiny realm of particles. And that world does not behave like tables, trees, oceans, or your own hands. It follows rules that seem broken when you first hear them. And one of those rules helped launch one of the boldest parallel universe ideas ever proposed. In quantum physics, a particle can exist in a spread of possibilities before a measurement. That is called superposition, which really just means multiple possible states are described at once. A particle can behave like it takes many paths before you check what happened. The strange part is that the math predicting this behavior works extremely well. Phones, lasers, and modern electronics all depend on quantum theory being deeply right. For a long time, many physicists used a practical attitude. The math worked, experiments matched it, and that was enough to keep building science. But one question never went away. When a measurement happens, why do we see one result instead of all possibilities at once? What exactly becomes real and what happens to the options that seem to disappear? In 1957, a young physicist named Hugh Everett III gave a shocking answer. Maybe nothing truly disappears. Maybe the wave of possibilities does not collapse into one outcome at all. Maybe every outcome continues, but in separate branches of reality. In that picture, when quantum events happen, the world does not choose once. It divides into many consistent histories. That idea became known as the many worlds interpretation. What scientists expected before this was simple. One event happens, one result becomes real, and the unused possibilities are gone. Whatever it said instead was much stranger. The unused possibilities might still exist, just not in the branch where you are standing. Why does that matter so much? Because this is not a fantasy added on top of bad science, and this is an attempt to explain what one of the most successful theories in human history actually means. Quantum mechanics predicts real things with amazing accuracy. So when its math seems to allow many branches of reality, scientists cannot dismiss that lightly. Still, we need to stay careful. Many worlds is called an interpretation for a reason. It does not change the basic quantum equations used in the lab. It changes how we understand what those equations are saying about reality. That means the math can remain powerful, while the meaning behind the math stays deeply debated. This is one of the first places where people get fooled by headlines. They hear that quantum physics allows many worlds and think proof has already arrived. But the honest version is subtler. Quantum theory gives space for that possibility. It does not yet give a direct, universally accepted measurement that forces everyone to accept many worlds as the only answer. Even so, the idea keeps its grip because the alternative is also strange. If many worlds sounds unbelievable, so does the idea that a measurement somehow makes one reality appear while all others vanish. In other words, physics is not choosing between a normal answer and a crazy answer. It is choosing between different kinds of weird, and scientists are trying to see which weirdness fits nature best. Here is the pattern that will repeat again and again tonight. Scientists begin with an expectation, then nature gives them something else, then the gap matters because the gap opens a larger question. With quantum physics, the expectation was one outcome becoming real in a simple way. The actual situation is that the equations leave room for far more than that. Would you want to know if another version of your life exists in some branching reality right now? And if you would, what question would you ask that other version first? Tell me below, and if this kind of honest mystery is your thing, like the video and subscribe for more. Now let's jump from the smallest scale to the largest. In the late 1970s and early 1980s, physicists were wrestling with major problems about the early universe. Why does space look so flat on huge scales? Why does one side of the sky look so similar to another side far beyond easy contact? Why is the large universe so smooth when the beginning should have been rougher? In 1980, physicist Alan Guth introduced a powerful idea called cosmic inflation. The simple version is that the early universe may have gone through a burst of expansion so fast it almost breaks imagination. Not just fast like an explosion, fast like space itself swelling at an extreme rate for a tiny fraction of a second. That burst could smooth out the cosmos and explain why distant regions look strangely alike. At first, inflation was built to solve a specific puzzle. Scientists expected a universe whose early conditions would leave more obvious large-scale mess. Instead, the cosmos looked smoother and more orderly than expected. Inflation offered a neat answer. If a tiny patch expanded wildly fast, then the giant universe we see today could come from one once-connected small region. So far, that sounds like one universe getting a smart explanation. But later work pushed the idea further. In some versions, inflation does not stop everywhere at the same time. One region can stop inflating and become a universe like ours, while other regions keep expanding and keep making more bubble universes. This is where the story moves from a useful early universe theory to a possible multiverse machine. Think of water beginning to boil. Bubbles appear here, then there, then somewhere else. Each bubble has its own boundary and grows in its own local space. Some inflation models suggest reality may work a bit like that on an unimaginably larger scale. Our universe could be one bubble among many, each cut off from the others by constantly expanding space. That shift matters for a very simple reason. Scientists expected inflation to explain one universe more clearly, but some of its deeper versions naturally lead to many universes, and those other universes might not just be distant places in ordinary space. They may be regions so separated by cosmic expansion that no signal from them can ever reach us. Now we hit another honest limit. Does inflation prove parallel universes? No, it shows that respected physics can generate them as a serious consequence. That is still important because it means the multiverse is not just a fun story made after the fact. It can grow out of the same theory used to explain features of the early universe. Physicist Andre Linde became one of the major voices behind this broader picture. His work helped make eternal inflation a serious subject. Eternal inflation means the larger process never fully ends everywhere. New bubble universes can keep forming while the background expansion goes on and on. And if that picture is correct, reality may produce universes the way a tree produces leaves again and again. And here, the emotional weight of the idea really starts to hit. If there are many bubble universes, they may not all share our laws of nature. Some could have different particle masses, different strengths of forces, or conditions where stars never form at all. Others might be closer to ours. The point is not that scientists have visited them. The point is that physics has built a serious doorway to imagine why our universe has the specific rules it does. Why does that matter to you? Because it changes the meaning of the biggest question. Maybe the laws of our universe are not the only possible laws. Maybe we see this set because we live in a bubble where these rules allow structure, chemistry, stars, and life. That idea is controversial, but it is one reason the multiverse keeps appearing in serious debate. Then came the sky maps, and with them, a fresh wave of excitement. In 2013, the European Space Agency released major results from the Planck spacecraft. Planck had made the most detailed map ever of the cosmic microwave background, the oldest light we can see. Overall, Overall, the results strongly supported the standard picture of cosmology, but buried inside that success were odd features that would not sit quietly. One of the most discussed was a strange cold spot in the sky. Another was a kind of asymmetry, a mismatch between large regions where scientists expected a better balance. Planck also found that some very large-scale fluctuations were weaker than expected. These were not huge movie-style tears in reality. They were subtle, statistical, stubborn irregularities in the oldest light of the cosmos. And this is where the phrase stunned scientist really does fit, but not in the cheap headline way. Planck was supposed to sharpen the standard model of cosmology, and it did. Yet the same precision that strengthened the model also revealed a few places where the fit looked imperfect. Scientists expected cleaner agreement on the biggest scales. Instead, they found clues that either pointed to rare cosmic luck, unseen effects, or maybe something deeper. The European Space Agency did not say, "We found a parallel universe." That matters. What ESA said was more careful. Planck's map confirmed the standard model very well overall, yet also showed peculiar, unexplained features that might require new physics. That phrase, new physics, is important because it means the current rulebook may not tell the whole story. One especially striking detail involved very large angular scales. Planck reported that on scales around 5 degrees across the sky, the signal was about 10% weaker than expected. The full moon spans about half a degree in the sky. So this was not a tiny dot. And this was a broad weakness spread across a huge region of the ancient light background. Now we repeat the pattern again. Expected, the oldest light should line up smoothly with the standard picture on those large scales. Actual, some large-scale features looked off, including the cold spot and weaker than expected fluctuations. Why it matters: if the early universe carries a scar or mismatch that normal cosmology cannot easily explain, then we may need a bigger picture, and for some scientists, a bigger picture can include the multiverse. One bold suggestion was that our universe might once have interacted with another bubble universe. If two bubble universes formed near each other in a larger inflationary background, maybe they could leave traces. A collision long ago might mark the cosmic microwave background with unusual patterns. And that idea caught attention fast because it sounded like exactly the kind of clue people had been waiting for. A bruise in the oldest light from a hit before history fully began. But science is not kind to easy excitement. A dramatic explanation must survive brutal checking. That is why later work on polarization mattered so much. Polarization is another property of light, and it gives scientists a partly independent look at the same ancient background. If the anomalies were deeply real in a new physics way, polarization might help confirm them. In 2019, ESA reported that Planck had found no new evidence for the anomalies in the polarization data. That does not mean the earlier strange features were fake. It means the second line of support was weaker than some people hoped. The anomalies were not strongly reinforced by this added check. And once again, the story moved away from proof and back into uncertainty. This is one of the most important lessons in the whole subject. People often think science works by one huge discovery followed by instant certainty. Real science is usually messier. A strange clue appears, people rush in, the clue gets tested from another angle, and the answer becomes less dramatic but more real. Sometimes the mystery survives, sometimes it shrinks, sometimes it changes shape without fully disappearing. The Planck anomalies are a perfect example of that. Scientists expected clearer confirmation if those odd signals pointed to deep new physics. What they actually got was ambiguity. Some anomalies remained interesting, but the polarization results did not deliver a knockout blow. So the multiverse stayed possible, not proven, and careful cosmologists kept their hands off the victory bell. Do you think a scar in the oldest light of space sounds like evidence or just a pattern our brains want to turn into a story? Say what you think in the comments. And if you like mysteries that get harder the closer we look, subscribe and keep going with me. Now we travel from the deep sky to one of the strangest places on Earth. Antarctica is cold, remote, and brutal, but it is also useful for physics. Above that frozen continent, an experiment called Anita flew on a balloon and listened for signs of ultra-high energy particles. Its full name is much longer, but the simple idea is easier. Use the ice, the air, and clever instruments to catch strange signals from the cosmos. Anita was especially interested in neutrinos. Neutrinos are tiny particles that barely interact with matter. They can pass through planets almost as if the planets are thin smoke. That makes them hard to detect, but it also makes them powerful messengers from violent cosmic events. If you can catch them, they tell stories from places light cannot easily explain on its own. Then came a few weird detections. Researchers reported upward-pointing events that looked surprising. In plain words, some signals seemed to come up from the ice at angles that were hard to fit with normal expectations. The Earth should make that route extremely difficult for known high-energy particles. So the first reaction was not parallel universe confirmed. The first reaction was something is odd here. Again, the pattern appears expected. Known particle physics should make those upward events very unlikely. Actual, a small number of events looked stubbornly hard to explain. Why it matters: when data refuses to sit inside the current model, scientists have to test whether the model is incomplete, the data is misunderstood, or the rare event is still possible after all. Every strange reading is a fork in the road. This is the point where headlines sprinted far beyond the evidence. Stories spread claiming NASA had found a parallel universe where time runs backward. That phrase traveled fast because it mixes science, shock, and just enough technical flavor to sound believable, but it was not an honest summary of what the evidence showed. Later coverage made this clear. NASA had not discovered a parallel universe, so where did the time-running backward idea come from? Some theorists discussed a model called a CPT symmetric universe. That phrase is technical, but the basic image is simpler. Our universe and a kind of partner universe might both emerge from the Big Bang in a mirrored way. From one side, time goes forward. From the other side, it could appear reversed. That is a serious theoretical idea, but it is still a theory. It was not a statement that Anita had seen this mirror universe directly, and that difference matters. A theory can be elegant, clever, and worth studying without being confirmed by one strange set of signals. Physics often builds several possible explanations before the evidence is strong enough to choose among them. Scientists involved with these questions kept pointing out that simpler answers still existed. Maybe the events came from unusual particle interactions. Maybe the ice or atmosphere shaped the signals in a tricky way. Maybe another detector would sort the confusion out later. The honest point was not that the mystery vanished. The honest point was that mystery is not the same thing as proof of another universe. This is frustrating for anyone who wants a fast answer, but it is also why science works. If physicists accepted every weird result as a cosmic revolution, the field would collapse into noise. Instead, they demand repeat detections, independent confirmation, stronger statistics, and multiple lines of evidence. One odd event can open a case, it cannot close one. That is why other experiments matter so much. At the South Pole, the ice cube detector studies neutrinos in a very different way. Future experiments will continue testing the limits of particle behavior at high energies. If the strange Anita-style events point to something real and new, related clues should appear elsewhere too. Nature does not usually hide forever if the effect is strong and the tools keep improving. So where does that leave the Antarctic story right now? In a fascinating but unfinished place. The expectation was clean particle behavior that fit the standard picture. The actual result was a few strange events that inspired bold ideas and even bolder headlines. Why it matters is simple. The more often reality surprises us at the edges, the less comfortable we become with the claim that we already understand the full map. Have you ever noticed how the wildest headlines usually appear before the strongest evidence does? If that bugs you too, hit like. And if you want the real version instead of the loud version, subscribe and stay with me for the next clue. Some multiverse ideas do not come from the early universe or strange sky patterns. They come from the structure of space itself. We live as if space has three directions, left and right, forward and back, up and down. Time gives us the flow from past to future. But some theories suggest that reality may contain more dimensions than the ones we directly feel. This sounds impossible until you remember that many real things are hidden from our senses. You cannot see radio waves with your eyes. You cannot feel neutrinos passing through you. You cannot notice the motion of atoms one by one. Science has taught us again and again that human senses are not the limit of what exists, so the idea of extra dimensions earns at least a hearing. At CERN, where the Large Hadron Collider smashes particles together at extreme energies, physicists have searched for hints of deeper structure. One reason is gravity. Gravity is incredibly weak compared with the other basic forces. A tiny magnet can fight the pull of the whole Earth on a paperclip. That mismatch has long bothered physicists, and one possible reason is that gravity may spread into hidden dimensions. If some of gravity leaks into places we do not normally experience, it would look weaker in our everyday world. That idea is not direct proof of another universe, but it suggests that the world we observe could be a slice of a larger reality. And once that becomes plausible, the old wall between our universe and something beyond starts to look less solid. The space around us may not be the whole stage after all. Scientists expected that if extra dimensions were real and reachable at high enough energies, particle collisions might reveal clues. Maybe energy would appear to vanish because something escaped detection into another dimension. Maybe heavy new particles would show up. Maybe even tiny black holes could flash into existence for a fraction of a second. Those sounds like huge ideas, but at their core, they are simply search targets built from theory. Here comes the check from reality. So far, the clean, accepted evidence has not appeared. The Large Hadron Collider has found many important things, including the Higgs boson, but not a confirmed portal to extra dimensions. That matters because science grows stronger when it meets resistance. If nature refuses the simplest versions of our boldest ideas, scientists have to refine the ideas or let them go. This is another place where people often misunderstand the word evidence. No detection at CERN does not prove hidden dimensions are impossible. It means the easier, more obvious versions are under pressure. Maybe the energy is not high enough. Maybe the clues are subtler. Maybe the idea is wrong. The search narrows the map even when it does not reveal the treasure. And this narrowing matters because the multiverse is not one single claim. It is a family of ideas: quantum branching, bubble universes from inflation, mirror universes from symmetry, hidden worlds and extra dimensions. Some of these could be wrong while others survive. When people ask, Are parallel universes real? They often mean one thing, but physics is actually testing several different roads. Now, the tone shifts from what happened to what is happening. Right now, scientists are still building better ways to test the largest questions in cosmology. The European Space Agency's Euclid mission is mapping galaxies across huge stretches of space and time. Its job is not to chase cheap multiverse headlines. Its job is to measure the growth and geometry of the universe with extreme care. Why does that matter for parallel universes? Because if our universe is one region inside a larger reality, that larger reality might leave fingerprints, not dramatic portals, not glowing rips in the sky, tiny statistical effects, subtle patterns in cosmic structure, odd alignments, or clues in how the universe expanded. Better maps mean smaller hints become easier to test. At the same time, scientists keep studying the cosmic microwave background with new tools and future plans. The oldest light in the universe still matters because it is a direct message from the early cosmos. If something disturbed our universe before stars existed, that light may still carry the trace. That is why researchers care so much about temperature patterns, polarization, and every tiny mismatch between observation and theory. A faint clue in old light can change the story of everything. Quantum experiments are moving too. Researchers keep pushing the size and complexity of systems that can show quantum behavior. They test superposition in larger objects, sharpen control over entanglement, and ask where the boundary lies between the quantum world and normal daily experience. Every successful experiment confirms that the underlying strangeness is real. The argument is not about whether quantum weirdness exists, it is about what that weirdness says about the shape of reality. This is one reason the parallel universe idea never fully goes away. The small world hints at branching. The early universe hints at bubble creation. The largest sky map hints that the standard picture may not explain every feature perfectly. High-energy physics asks whether hidden dimensions or deeper structures are waiting beyond current reach. Different tools keep circling the same cliff edge from different directions. None of that gives us a final answer, but it gives us something almost as important, a live scientific question. This is not a dead theory sitting in a dusty corner. It is an active pressure point in modern physics, a place where math, observation, and philosophy collide, a place where every new result has the power either to shrink the dream or sharpen it. If the next big clue shows up in your lifetime, where do you think it will come from first? From a better sky map, a particle detector, or a quantum lab? Drop your guess in the comments and subscribe so you can say you were here before the answer landed. At this point, we should slow down and ask the blunt question clearly. Is there proof that parallel universes are real? If by proof you mean direct, confirmed, widely accepted evidence that forces the full scientific community to agree, the answer is no. That is the honest answer today. Anyone telling you otherwise is adding drama where the evidence still has gaps, but there is another question hidden inside that one. Is there enough serious reason for scientists to keep treating the idea as more than fantasy? There, the answer is yes. Quantum theory leaves room for many worlds. Inflation naturally opens the possibility of many bubble universes. Cosmic anomalies have pushed scientists to consider new physics, and strange particle events remind us that nature still has places where our confidence thins out. This balance is why the topic is so powerful. One side says, do not overclaim. The other side says, do not laugh too fast. The multiverse sits right in the middle of those warnings. It is too serious to dismiss as a joke. It is too unproven to sell as solved truth. That tension is exactly why physicists, writers, and the public keep returning to it. There's also a very human reason this question hits so hard. Parallel universes are not only about equations and telescopes, they touch memory, regret, choice, and possibility. People hear the idea and immediately think of other lives, missed chances, and different versions of themselves. Science is asking one thing, but the human heart hears another. That is part of why the subject spreads so fast. Still, the emotional pull can mislead us if we let it. We can start wanting the idea to be true so badly that any strange data feels good enough. That is dangerous. Good science does not care what story feels best. It cares what survives testing. The stronger the claim, the harder the evidence must hit, and here is the beautiful part. Even if the multiverse is never confirmed, the search still matters. To ask whether there are other universes is to ask whether our current picture is final or partial. It pushes science to test its limits. It forces better instruments, sharper math, and cleaner thinking. The hunt for deeper reality often teaches us even when the grand prize stays out of reach. Imagine what a real breakthrough would mean. If a future sky map found a pattern that matched a predicted bubble collision, textbooks would change. If quantum experiments somehow separated interpretations and strongly favored branching worlds, reality itself would feel different. If hidden dimensions showed up in a collider, our ordinary picture of space would crack open overnight. These are not small upgrades, these are worldview events. And that is why scientists are stunned, though maybe not in the way headlines sell it. They are stunned that modern physics keeps producing doorways to the same impossible sounding place. Not one doorway, many. Some are stronger, some weaker, some controversial, some elegant. But together they create a strange pattern. The universe we know may not be the full territory. Think about how wild that already is. For centuries, people argued about whether other planets even existed. Now we know there are worlds around other stars all across the galaxy. Ideas that once sounded outrageous sometimes become normal after the evidence builds. That does not mean every wild idea wins. It means the border between absurd and accepted moves when reality forces it to move. So maybe the wisest position is not belief and not dismissal. Maybe it is disciplined curiosity. Stay open enough to follow the clues. Stay skeptical enough to reject weak claims. Stay patient enough to let evidence mature. That is the posture science demands here, and it is harder than either blind trust or easy mockery. Right now, the case for parallel universes is not a solved case. It is a living file, thick with theory, scattered with hints, and marked by arguments that have not ended. Some clues have faded under rechecking, some ideas remain mathematically powerful, some observations keep nagging at the edges, the file is still open, and that alone tells you something important, because science closes the door on bad ideas all the time. And when a theory fails hard enough, it loses attention, funding, and respect. The multiverse has not vanished that way, it keeps returning because the underlying problems are real. Why quantum measurement works the way it does is real. Why inflation may generate many regions is real. Why some cosmic anomalies refuse easy comfort is real. If you have made it this far, then you already know the real twist. And the title sounds like a statement about proof. The truth is more unsettling than that. We do not have final proof, but we do have repeated pressure from the best tools we possess. And sometimes that kind of pressure is how revolutions begin, not with one clean shout, but with many careful whispers that keep pointing in the same direction. So now I want your answer. Which idea feels most convincing to you right now? Quantum, many worlds, eternal inflation, strange cosmic scars, hidden dimensions, or none of them at all? Subscribe and turn on notifications if you want more space mysteries told with the evidence kept intact. And share this with someone who loves the biggest questions but hates fake certainty. Thank you for watching. I really appreciate your curiosity. See you in the next one.